There is a particular kind of silence that exists nowhere on Earth, a silence so complete that it can be difficult to properly imagine, no matter how quiet a room we might find ourselves sitting in right now. It is the silence of true empty space, the vast, cold emptiness that fills nearly all of the universe between one star and the next. And somewhere within that silence, scattered throughout galaxies beyond counting, exist objects so powerful, so consequential to everything around them, that calling them merely powerful almost understates the case. And yet, despite everything they are capable of, these objects make no sound at all. They emit no light of their own. They simply exist, quietly in the dark, doing something to the universe around them that nothing else in all of creation can do. We are speaking, of course, of black holes. There is something worth sitting within this apparent contradiction before we go any further, because it sits at the very heart of everything this account will attempt to explore. We tend, quite naturally, to associate power with noise, with light, with some visible or audible signature of the forces involved. A star blazes. A supernova floods entire galaxies with light bright enough to outshine every other star within them combined. Even something as comparatively modest as a thunderstorm here on Earth announces its power through sound and light both, through the crash of thunder and the flash of lightning tearing across a darkened sky. A black hole does none of this. It does not blaze, it does not flash. It produces, in the most literal sense, absolutely nothing that our eyes or ears could ever directly detect on their own. And yet, within the specific region of space it occupies, a black hole exerts a gravitational influence so extreme that nothing, not light, not matter, not even the fastest thing the universe permits to travel, can escape it once it has crossed a certain boundary. This is not a small effect, confined to some minor corner of physics. It is one of the most extreme phenomena the universe is capable of producing, and it accomplishes all of this in complete, unbroken silence. To understand what a black hole actually is, it helps to set aside, for a moment, some of the more dramatic language often used to describe them. Language this very documentary's title admittedly borrows, and instead approach the subject with the same patient, careful curiosity we might bring to any other genuine mystery of the natural world. A black hole, in the simplest possible terms, is a region of space where gravity has become so overwhelmingly strong that it has fundamentally altered the very structure of space and time surrounding it. This gravitational strength does not come from anything exotic or mysterious in the composition of a black hole itself. It comes instead from an extraordinary concentration of mass, compressed into a volume of space far smaller than that same mass would ordinarily occupy. Consider for a moment what this actually means. Every object with mass, from the smallest pebble to the largest star, exerts some degree of gravitational pull on everything around it. Under ordinary circumstances, this pull remains limited by how spread out that mass actually is. Earth's gravity, considerable as it feels to us standing on its surface, remains gentle enough that a rocket with sufficient speed can escape it entirely, carrying astronauts safely beyond our planet's gravitational grip. But if you were to take all of Earth's mass and compress it down into a space roughly the size of a marble, without losing a single particle of that mass in the process, something remarkable would happen. The gravitational pull at the surface of that compressed marble would become so extreme that not even light, the fastest thing the universe allows to exist, would possess sufficient speed to escape it. This, in essence, is what a black hole represents. Mass compressed so completely, so extremely, that the resulting gravitational pull exceeds even the speed of light's own considerable velocity, at least within a certain boundary surrounding this compressed mass. And it is precisely this boundary, this specific distance from the black hole's center, beyond which escape simply becomes physically impossible, that astronomers call the event horizon. It is worth pausing here to clarify something important, something that will shape our understanding throughout the entirety of this account. The event horizon is not a physical surface, in the way the surface of a planet or a star represents an actual physical boundary, a place where solid or liquid material genuinely exists. There is no wall here, no membrane, nothing you could touch or collide with in any conventional sense. The event horizon is better understood as a kind of threshold, a specific point in space defined entirely by physics rather than by any physical substance, beyond which the mathematics governing escape velocity simply no longer permits a return. This distinction matters enormously because it helps explain something that might otherwise seem paradoxical. We cannot see a black hole directly, not because it is somehow cloaked or hidden by some special property of its own, but simply because, by definition, no light can travel outward from within its event horizon to ever reach our eyes, or our telescopes, or any instrument we might ever build. A black hole is not dark in the way a shadow is dark, an absence of light passing through an otherwise lit region. It is dark because the very light that might otherwise reveal it has become, in the most literal sense, trapped, unable to travel outward across that particular boundary, no matter how much time is allowed to pass. This raises a genuinely fascinating question, one that will guide much of what follows across the chapters ahead. If a black hole cannot be seen directly, if it produces no light and no sound of its own, how do we know black holes exist at all? How have scientists managed to study objects that are, by their very nature, invisible? The answer, as we will discover, lies not in observing the black hole itself, but in observing its considerable effects on everything around it, the way it bends light passing nearby, the way it influences the orbits of nearby stars, the way matter spiraling toward it can, under the right conditions, glow with tremendous, brilliant energy before finally disappearing across that same invisible threshold. It is worth addressing directly, too, the particular language this documentary has chosen for its own title, the description of black holes as monsters. This word carries an undeniable emotional weight, conjuring images of menace, of malevolent intent, of something actively hunting and destroying whatever crosses its path. It is important to understand clearly and directly that this framing, however evocative, does not reflect what a black hole actually is in any literal sense. A black hole has no intention. It does not hunt. It does not seek out victims or lie in wait or behave with anything resembling awareness or purpose. It is, in the most fundamental sense, simply gravity, an entirely natural, entirely predictable consequence of physics operating exactly as physics always does, only taken to an extreme intensity rarely encountered anywhere else in the universe. And yet, monster remains a useful word nonetheless, not because it accurately describes any hidden malevolence within a black hole, but because it captures something true about the experience of confronting something this overwhelming, this consequential, and this fundamentally beyond ordinary human intuition. We use the word not because black holes wish us harm, but because encountering the sheer scale of what they represent, gravity strong enough to trap light itself, mass compressed beyond anything we can properly picture, produces something close to the same awe and the same unease that the word monster has always been meant to evoke. This, then, is where our journey begins, not with drama, not with sound or light or anything our senses could readily detect, but with silence, complete and total, surrounding objects of such extraordinary gravitational power that they have reshaped our very understanding of space and time itself. Ahead of us lies the story of how such objects come to exist in the first place, born not from nothing, but from something considerably more familiar, the long, patient life and the sudden, dramatic death of a star far larger than our own quiet, steady sun. And the strangest thing about a black hole, as we will come to understand across the chapters ahead, is not what it destroys. It is what happens to everything that gets too close. To understand how something as extraordinary as a black hole comes to exist, we must first turn our attention away from darkness entirely and toward something considerably more familiar. A star, blazing with light, engaged in a struggle so fundamental to its existence that the star itself depends on this struggle continuing, unbroken, for as long as it hopes to remain a star at all. Every star in the night sky, our own sun included, exists in a state of continuous, delicate balance between two opposing forces, each pulling in a different direction, each entirely necessary for the star's continued survival. On one side stands gravity, the same fundamental force that holds planets in their orbits and draws falling objects toward the ground here on Earth, except within a star, gravity operates on a considerably larger and more consequential scale. Every particle of matter within a star exerts a gravitational pull on every other particle, and collectively, this pull works constantly, relentlessly, to compress the star inward, to draw its enormous mass toward an increasingly small, increasingly dense center. If gravity alone governed a star's behavior, the outcome would be swift and decisive. The star would simply collapse in on itself, its material crushed inward by its own weight, with nothing to prevent this collapse from continuing until the star's matter had been compressed into an extraordinarily small, extraordinarily dense form. But stars, at least for the greater portion of their lives, do not collapse in this way because gravity does not act alone. Opposing it, pushing outward with equal and often even greater force, is the tremendous energy released by nuclear fusion, occurring continuously within the star's core. Nuclear fusion within a star's core involves atomic nuclei colliding with such tremendous force and frequency that they combine to form heavier elements, releasing, in the process, enormous quantities of energy. This energy radiates outward from the core in the form of both light and heat, creating an outward pressure that, for most of a star's life, precisely balances the inward pull of its own gravity. This balance between gravity's relentless pull inward and fusion's powerful push outward is what allows a star to maintain a stable size and shape across the enormous stretches of time most stars spend simply existing, neither collapsing nor exploding, but burning steadily, predictably, sometimes for billions of years at a stretch. Our own sun exists in precisely this kind of balance right now, and has for roughly 4.5 billion years already, its core continuously fusing hydrogen into helium, releasing the light and warmth that reaches us here on Earth, some 93 million miles away, while gravity continues its own steady, patient work, held reliably in check by this same ongoing fusion. This balance feels permanent from our particular vantage point, watching the sun rise and set with such reliable regularity, but it is not permanent. No star's balance lasts forever because every star eventually exhausts the fuel that makes this balance possible in the first place. A star's core over the course of its life gradually converts its available hydrogen into helium, and eventually, depending on the star's particular mass, may continue fusing helium into still heavier elements as well, carbon, oxygen, and in sufficiently massive stars, elements heavier still. But this process cannot continue indefinitely. Each stage of fusion requires progressively higher temperatures and pressures to sustain, and eventually, every star reaches a point where it simply lacks the fuel or the necessary conditions to continue generating the outward pressure that has, until this point, successfully held gravity's relentless pull in check. What happens next depends enormously on the star's original mass, a distinction worth understanding clearly, because it explains precisely why some stars end their lives in relatively modest, unremarkable fashion, while others produce some of the most violent, most consequential events the universe is capable of generating. Our own sun, a relatively modest star by the standards of the universe as a whole, will eventually exhaust its usable fuel, expand into a considerably larger but cooler star known as a red giant, and eventually shed its outer layers entirely, leaving behind a small, dense remnant called a white dwarf, a fascinating object in its own right, but one that will never possess anywhere near sufficient mass to become a black hole. The reason for this distinction lies in a critical threshold, one that separates stars destined for a relatively gentle ending from stars destined for something considerably more dramatic. A star's own mass, it turns out, is the single most important factor determining not just how it lives, but how it ultimately dies, and what, if anything, it might leave behind once its fusion has permanently ceased. For sufficiently massive stars, generally understood to require at least somewhere in the range of 8 to 10 times the mass of our own sun, though the precise threshold remains an area of continued scientific refinement, the ending unfolds quite differently and considerably more violently than anything a star like our own sun will ever experience. As such, a massive star exhausts each successive stage of nuclear fuel, fusing progressively heavier elements within its core in a desperate attempt to continue generating the outward pressure needed to resist its own gravity. It eventually reaches a point of genuine crisis. Once a massive star's core has fused its way to iron, it encounters a fundamental limit, because fusing iron into anything heavier does not release energy the way earlier stages of fusion did. Instead, it consumes energy, offering no further outward pressure capable of resisting gravity's relentless pull. At this precise moment, the delicate balance that had sustained the star across millions of years of its life finally, catastrophically, fails. With no remaining outward pressure to resist it, gravity takes over completely, and the star's core collapses inward with extraordinary speed, a process unfolding not across years or even days, but within a matter of mere seconds, an entire star's core crushing inward upon itself with a speed almost impossible to properly convey through ordinary language. This sudden, catastrophic collapse triggers one of the most powerful and most visually spectacular events the universe is capable of producing. A supernova, an explosion of such tremendous energy that, for a brief period, a single dying star can outshine the combined light of every other star within its entire host galaxy. The outer layers of the star, no longer held in place by anything capable of resisting the shockwave generated by this sudden core collapse, are blasted outward into surrounding space with tremendous force, scattering material, including many of the heavier elements forged within the star's core across its lifetime, across vast distances, material that will, in time, become incorporated into future generations of stars, planets, and, in at least one remarkable case we have already explored in considerable detail, the very world we call home. But what remains behind, at the very center of this spectacular explosion, depends once again on precisely how much mass the original star possessed. For stars within a certain mass range, the collapsing core comes to rest as an extraordinarily dense object called a neutron star, its matter compressed to a density almost impossible to properly imagine, a single teaspoon of neutron star material weighing, quite literally, billions of tons. But for the most massive stars of all, generally understood to require an original mass upward of roughly 20 times that of our own Sun, even this extraordinary density proves insufficient to halt the ongoing collapse. Gravity, in these most extreme cases, continues its relentless work even beyond the point where a neutron star would otherwise form, compressing the star's remaining core smaller still, past every limit that any other force in the universe is capable of resisting. It is precisely here, in this most extreme of all possible stellar endings, that a black hole is finally born. Not through any special, exotic process unrelated to everything else we have described, but through the same fundamental struggle between gravity and pressure that governs every star's entire existence, carried, in this particular case, to its ultimate, most extreme possible conclusion. A massive star, having spent millions of years successfully resisting its own gravity through the continuous energy of nuclear fusion, finally runs out of the fuel required to continue that resistance, and gravity, patient and relentless, finally, completely wins. Ahead of us lies the question of exactly what this victory actually means, what it looks like when gravity becomes strong enough not merely to compress a star's remaining core, but to trap light itself within an invisible, inescapable boundary, a threshold from which nothing, once crossed, can ever return. To properly understand what makes a black hole so fundamentally different from any other object in the universe, it helps to begin with a concept considerably more familiar, one you have likely encountered before, perhaps without ever fully considering its deeper implications: escape velocity. Escape velocity refers to the minimum speed an object must reach in order to break free from another object's gravitational pull entirely, traveling fast enough that gravity, however persistently it continues tugging backward, can never quite succeed in pulling that object back down. Here on Earth, this threshold is considerable but entirely achievable using conventional rocket technology, requiring a spacecraft to reach a speed of roughly 25,000 miles per hour before it can break free of our planet's gravitational grip and continue outward into space, no longer bound to eventually fall back toward the ground. This threshold, it turns out, depends entirely on two factors: how much mass the object in question possesses, and how compactly that mass happens to be arranged. Earth, despite its considerable overall mass, remains spread across a large enough volume that its escape velocity, while significant, remains well within the reach of conventional rocket propulsion. But if that same mass were compressed into a considerably smaller space, the gravitational pull at the surface of that now more compact object would increase substantially, and the corresponding escape velocity required to break free from it would increase correspondingly as well. Consider, for comparison, a neutron star, the extraordinarily dense stellar remnant briefly introduced in our previous chapter. A neutron star typically contains a mass comparable to our own Sun, compressed into a sphere only about 12 miles across, a compactness almost impossible to properly picture given the scale of mass actually involved. The escape velocity required to break free from a neutron star's surface reaches roughly half the speed of light itself, a figure that should immediately convey just how extreme these objects truly are, even before we arrive at black holes specifically. And this brings us quite naturally to the question that sits at the very heart of what makes a black hole in the first place. What happens when an object becomes so compact, so extraordinarily dense, that its escape velocity does not merely approach the speed of light, but actually exceeds it entirely? Here we encounter something the universe treats as an absolute, unbreakable limit. According to everything we currently understand about physics, nothing with mass can ever travel at or beyond the speed of light. Light itself represents an ultimate cosmic speed limit, the fastest that anything, whether matter or information, is ever permitted to travel through the universe. This is not merely a practical limitation, reflecting some current gap in our engineering capabilities that future technology might eventually overcome. It is a fundamental feature of the universe's own underlying structure, one confirmed through more than a century of careful experimentation and observation. If an object becomes compact enough that its escape velocity would need to exceed the speed of light in order for anything to break free from its surface, then nothing, quite literally nothing, can ever actually achieve that escape. Not a spacecraft, however powerful its engines, not any form of matter, however energetic. And crucially, not light itself, despite being the very thing that defines this ultimate cosmic speed limit in the first place. Once an object crosses this particular threshold of compactness, light emitted from its surface, or from anywhere within the boundary defined by this threshold, cannot travel outward and away. It remains trapped forever, drawn back by a gravitational pull that not even the fastest possible speed can overcome. This boundary, the precise distance from an object's center at which escape velocity exactly equals the speed of light, is what we call the event horizon, the same term introduced briefly in our opening chapter, but one that deserves considerably more careful examination now that we properly understand the physics underlying it. It is worth emphasizing again, with particular care, that the event horizon does not represent any kind of physical surface or barrier in the conventional sense. There is no solid boundary here, no wall an approaching spacecraft might collide with, no membrane separating one region of space from another in any tangible way. The event horizon is instead a purely mathematical threshold, a specific distance calculated based on an object's mass, beyond which the physics of escape velocity simply no longer permits any possibility of return. Space itself continues uninterrupted across this boundary. What changes is not the substance of space, but the fundamental relationship between that space and the possibility of ever leaving it again. This distinction carries a particular consequence worth sitting with carefully, because it complicates something that might initially seem like a straightforward absolute rule. We often hear it said that nothing can escape a black hole, full stop, an absolute, unbreakable law of the universe. And in the most immediate, most direct sense, this remains entirely true. Nothing that has already crossed the event horizon can subsequently travel back outward across that same boundary. But this statement requires a certain amount of careful qualification once we begin considering more subtle physics, including processes that occur not through anything crossing the horizon outward, but through more exotic quantum mechanical effects operating at the very edge of the horizon itself, phenomena we will explore in considerably greater depth much later in this account, once we have properly built toward the more advanced physics required to understand them. For now, it is enough to understand the essential foundational truth. Once any object, whether a spacecraft, a wandering asteroid, or a single particle of light, crosses the event horizon of a black hole, it cannot, through any conventional means, ever travel back outward across that same boundary again. This raises a particularly important question, one that will occupy a considerable portion of the chapters still ahead of us. If gravity, in its ordinary, everyday sense, simply describes a force pulling objects toward one another, how does it come to produce an effect this extreme, this absolute? The answer requires us to set aside, at least partially, the more intuitive picture of gravity most of us carry from ordinary experience, and turn instead toward a considerably more sophisticated understanding, one first properly articulated by Albert Einstein in the early 20th century. Einstein's description of gravity differs fundamentally from the simpler picture offered by earlier physics, one in which gravity was understood essentially as a force, not unlike magnetism, pulling objects directly toward one another across the empty space separating them. Einstein proposed something considerably more elegant and considerably stranger once properly understood. Rather than treating space and time as a fixed, unchanging backdrop against which objects simply move, subject to various forces acting upon them, Einstein suggested that space and time themselves form a single, interconnected fabric, one capable of being bent, warped, and curved by the presence of mass and energy within it. Under this understanding, gravity is not, strictly speaking, a force pulling objects together in the way we might intuitively imagine. It is instead the natural consequence of objects following the straightest possible path available to them through a region of space and time that has itself been curved by the presence of some massive object nearby. A planet orbiting a star is not being continuously pulled inward by some invisible tether. It is simply following the curved geometry of space and time, reshaped by the star's own considerable mass, a path that happens, given this curvature, to trace a stable, ongoing orbit rather than a straight line. This reframing, strange as it may initially seem, becomes essential once we begin considering objects as extreme as black holes. Near a black hole, mass has become concentrated so completely, so extraordinarily, that the surrounding curvature of space and time itself becomes correspondingly extreme, curving so sharply near the event horizon that every possible path available to any object, including light itself, bends inevitably inward toward the black hole's center, with no path remaining available that leads back outward again. Gravity, understood this way, is no longer simply a force pulling objects into a kind of cosmic prison. It is something closer to a fundamental reshaping of the very geometry through which objects are able to move at all, a reshaping so severe that, beyond a certain boundary, outward movement itself, in any direction, along any path, simply ceases to remain among the possibilities the universe allows. It is this deeper, considerably stranger understanding of gravity curved spacetime rather than a simple inward pull that will guide us through everything still ahead in this account, as we turn now toward the question of what an actual approach toward a black hole might genuinely look like, and what a hypothetical traveler, drawing ever closer to this strange and absolute boundary, might actually experience along the way. Let us imagine, for a moment, something no human being has ever actually done, and likely never will in any of our own lifetimes. A slow, deliberate approach toward a black hole, aboard a hypothetical spacecraft equipped with instruments capable of observing everything unfolding around it, and crucially, capable of transmitting what it observes back to those of us watching safely from a considerable distance away. This thought experiment, speculative as it necessarily is, offers something genuinely valuable, a way of making tangible the strange, often counterintuitive physics we have spent our previous chapters carefully building toward. Picture this spacecraft then beginning its approach from a considerable distance, far enough away that the black hole's gravitational influence remains relatively modest, not unlike the gravitational pull any ordinary massive object might exert at a similar distance. At this stage, remarkably, very little would appear unusual at all. The black hole itself would remain invisible, precisely as we would expect given everything discussed in our previous chapters, a region of complete darkness against the surrounding backdrop of distant stars, distinguishable from ordinary empty space only by its considerable gravitational effect on anything passing nearby. As the spacecraft continued its approach, however, drawing gradually closer to this dark, invisible region, something increasingly strange would begin to unfold around its edges, a consequence of the curved spacetime we explored in our previous chapter, now becoming pronounced enough to produce visible, dramatic effects. Light from stars positioned behind the black hole, from the spacecraft's particular vantage point, would begin to bend around it, curving along the warped geometry of space itself, rather than continuing in the straight lines we ordinarily associate with light's behavior. This bending, known as gravitational lensing, would produce an effect increasingly strange and increasingly beautiful the closer the spacecraft drew, distant stars appearing to smear and distort into curved arcs of light, sometimes even appearing to duplicate the same star's light, reaching the spacecraft's instruments along multiple different curved paths simultaneously, each one bent by a slightly different degree around the black hole's considerable gravitational influence. This lensing effect would grow increasingly extreme as the spacecraft continued its approach, the darkness at the center of this warped, distorted starfield growing correspondingly larger, not because the black hole itself had grown in any physical sense, but because an increasingly wide region of surrounding space had become sufficiently curved to bend light around it, expanding what astronomers call the black hole's shadow. A concept we will explore in considerably greater depth in a chapter still ahead of us. But visual distortion, however striking, would represent only one part of what our hypothetical spacecraft and those observing its journey from a safe distance would begin to notice. Something considerably stranger, considerably more fundamental to the very nature of the journey itself, would also begin to unfold, something involving not merely how things appeared, but how time itself seemed to behave, both for those aboard the approaching spacecraft, and for anyone watching its journey unfold from safely outside the black hole's most extreme gravitational influence. Here, it becomes essential to draw a careful distinction between two very different perspectives on the very same unfolding event, a distinction that sits at the heart of some of the strangest, most genuinely counterintuitive physics involved in any close approach to a black hole. Consider first the perspective of an observer watching this hypothetical spacecraft's approach from a considerable, entirely safe distance, perhaps from a research vessel stationed well beyond any significant gravitational influence. From this distant observer's perspective, something curious would begin to happen as the approaching spacecraft drew closer and closer to the event horizon. Rather than appearing to accelerate directly toward this boundary and cross it, as ordinary intuition might suggest, the spacecraft would instead appear to slow down, its motion becoming increasingly sluggish the closer it approached. Any light or radio signals it continued transmitting arriving at increasingly stretched, increasingly delayed intervals, until from this distant observer's perspective, the spacecraft would appear to approach the event horizon with ever-decreasing speed, seemingly never quite completing its final approach, appearing in effect to freeze in place, indefinitely, just short of actually crossing the boundary itself. This apparent freezing, however, tells only part of the story, and it is crucial to understand that it reflects something about how information and light travel through increasingly curved spacetime, rather than reflecting what the spacecraft, and anyone hypothetically aboard it, would actually experience firsthand. From the spacecraft's own perspective, assuming any instruments or hypothetical crew aboard could somehow survive the increasingly extreme conditions involved, no such freezing would occur at all. The spacecraft would continue its approach at what felt, from its own local, immediate perspective, like an entirely ordinary, continuous passage of time, crossing the event horizon in what would feel, to anyone aboard, like a perfectly unremarkable, uneventful moment, indistinguishable in any locally noticeable way from the moments immediately preceding it. This distinction between what a distant observer perceives and what someone actually experiences locally represents one of the most genuinely important concepts in this entire account, one we will need to carry carefully with us throughout the chapters still ahead. It is not that time is somehow lying, or that one of these two perspectives is somehow more correct than the other. Both perspectives remain simultaneously, genuinely true, each accurately describing the exact same underlying physical event, but from two fundamentally different vantage points, each shaped by its own particular relationship to the black hole's increasingly extreme gravitational influence. It is worth directly addressing and directly setting aside a particular misconception that sometimes arises from this apparent freezing effect, one that might suggest an approaching object somehow becomes permanently suspended at the event horizon, frozen forever in a kind of eternal, unchanging limbo. This is not, in fact, what actually occurs, at least not in any straightforward sense reflecting the object's own genuine physical fate. The apparent freezing observed by a distant onlooker reflects the increasingly extreme stretching of light and information traveling outward from the approaching object, light taking longer and longer to climb back out of the increasingly steep gravitational curvature surrounding the black hole, eventually stretching so extremely that any light emitted very near the event horizon would require, from a distant observer's perspective, an amount of time so vast that it would, for all practical purposes, never actually arrive at all. The object itself, meanwhile, from its own local perspective, would have long since crossed the boundary, its own experience of time continuing forward entirely normally, entirely unaware of any such apparent freezing occurring from any other point of view. This brings us finally to the deeper meaning behind the phrase so often used to describe the event horizon, a phrase that has, by this point in our account, hopefully accumulated considerably more genuine physical meaning than when we first briefly encountered it several chapters ago, the point of no return. This phrase captures something genuinely, precisely accurate about the event horizon's fundamental nature, though perhaps not in quite the dramatic, instantaneous sense the phrase might initially suggest. There is no dramatic barrier here, no sudden wall an approaching spacecraft might collide with in any physically noticeable way. From the perspective of anything actually crossing this boundary, the moment itself would likely pass entirely unnoticed, indistinguishable, at least locally, from any other ordinary moment of travel through otherwise empty space. And yet, despite this apparent lack of any dramatic, immediately noticeable transition, everything about that object's future has, in this same unremarkable moment, become permanently, irreversibly altered. Every possible path now available to it, every direction it might attempt to travel, every conceivable trajectory its engines might attempt to follow, leads only further inward, deeper toward the black hole's center, with no path remaining, none whatsoever, that leads back outward again. This is the genuine, precise meaning behind the point of no return, not a dramatic, visible barrier, but a quiet, unremarkable threshold, crossed perhaps without any immediate awareness at all, beyond which return has nonetheless become entirely, permanently impossible. What then might actually lie beyond this quiet, unremarkable threshold, for anything or anyone that continues its journey forward, deeper into the black hole's increasingly extreme gravitational influence? This question will occupy us considerably later in our account, once we have properly built toward the physics necessary to even begin approaching it responsibly. For now, our attention turns instead toward a related, equally strange consequence of everything we have discussed across this chapter: the peculiar, genuinely fascinating relationship between gravity and the passage of time itself, a relationship that extends considerably beyond the immediate vicinity of a black hole's event horizon, revealing something profound about the fundamental nature of time throughout our entire universe. In our previous chapter, we encountered something genuinely strange. A distant observer watching an approaching spacecraft appear to slow, almost to the point of freezing, as it drew nearer and nearer to a black hole's event horizon, even as anyone aboard that same spacecraft would have experienced nothing unusual at all, their own passage of time continuing forward in what felt to them like an entirely ordinary, unbroken sequence of moments. This apparent contradiction, two equally true but seemingly incompatible descriptions of the very same event, deserves considerably more careful examination, because it touches on something Albert Einstein first properly understood a little over a century ago, a discovery that would eventually prove essential to everything we now understand about black holes. The fact that time itself is not the fixed, universal constant our everyday experience so strongly suggests it must be. Most of us move through our daily lives operating under an entirely reasonable, entirely intuitive assumption that time passes at the same steady rate for everyone, everywhere, regardless of circumstance. A clock ticking in one room, we naturally assume, ticks at precisely the same rate as an identical clock ticking in any other room, anywhere else in the world, or indeed anywhere else in the universe. This assumption serves us perfectly well across the ordinary scale of human experience, and for good reason. The effects that would reveal this assumption to be, strictly speaking, incorrect remain far too small to notice under any conditions we typically encounter in daily life. Einstein's theory of general relativity, however, revealed something genuinely remarkable once we begin considering more extreme conditions involving either very high speeds or, more relevant to our current purposes, very strong gravitational fields. According to this theory, time does not in fact pass at a fixed, universal rate for everyone, everywhere. Instead, the rate at which time passes depends, in part, on the strength of the gravitational field an observer happens to occupy, a phenomenon known as gravitational time dilation. To understand this concept properly, it helps to think of time not as some separate, independent quantity, ticking away in the background regardless of anything else happening in the universe, but rather as something intimately connected to the very same curved spacetime fabric we explored in earlier chapters, the same fabric that gravity itself represents a curvature within. Just as mass curves the geometry of space, causing objects to follow curved paths rather than straight lines, it similarly curves the geometry of time, causing clocks positioned within stronger gravitational fields to tick more slowly, relative to clocks positioned within weaker gravitational fields than we might otherwise intuitively expect. This effect, remarkably, has been directly measured and confirmed here on Earth itself, through experiments precise enough to detect even the exceedingly small differences in gravitational strength between. For instance, a clock positioned at sea level and an otherwise identical clock positioned atop a tall mountain, where Earth's gravitational pull is very slightly weaker. The clock positioned lower within Earth's slightly stronger gravitational field does indeed tick very slightly slower than its counterpart positioned higher up, exactly as general relativity predicts, though the actual difference involved remains far too small for any human being to notice without extraordinarily precise instruments specifically designed to detect it. Near a black hole, however, where gravitational fields become vastly more extreme than anything found naturally here on Earth, this same effect becomes dramatically, unmistakably significant, rather than remaining a subtle effect requiring specialized instruments to detect it all. As our hypothetical spacecraft from the previous chapter continued its approach toward the event horizon, moving into progressively stronger and stronger gravitational fields, time itself, from the perspective of any distant observer watching from farther away, would appear to pass increasingly slowly for the approaching spacecraft, the difference growing more and more pronounced the closer the spacecraft drew to the boundary itself. This is precisely what produced the apparent freezing effect described in our previous chapter. It was not that the spacecraft had somehow malfunctioned or that some external force had begun physically restraining its motion. It was rather a direct, genuine consequence of gravitational time dilation, growing so extreme near the event horizon that time itself, from a distant observer's perspective, appeared to slow toward what would eventually become, in the mathematical limit, a complete stop, precisely at the boundary of the event horizon itself. It is worth emphasizing again with particular care, something touched upon briefly in our previous chapter, because it represents one of the most commonly misunderstood aspects of this entire phenomenon. This apparent slowing of time does not reflect anything happening to time itself, from the perspective of whoever or whatever is actually experiencing it locally. Aboard our hypothetical spacecraft, nothing about the passage of time would feel unusual in any way. A clock aboard the spacecraft would continue ticking at precisely the same rate it always had, from the perspective of anyone observing that clock directly alongside it within the very same local environment. Time dilation is not something one experiences directly, in the sense of feeling time itself somehow slowing down around oneself. It is instead something that becomes apparent only when comparing one's own local experience of time against the experience of someone else, positioned within a different gravitational field entirely, each perspective remaining entirely valid and entirely consistent within its own particular frame of reference. This distinction helps clarify a common misconception worth directly addressing before we continue further: the notion that an object approaching a black hole's event horizon somehow becomes literally, physically frozen in place at that boundary, suspended there indefinitely, unable to ever actually complete its crossing. This is not, in fact, what general relativity actually predicts, despite how the apparent freezing effect, observed from a considerable distance, might initially seem to suggest exactly this. The freezing effect observed by a distant observer reflects the increasingly extreme delay experienced by any light or information attempting to travel outward from the approaching object, not any actual halting of the object's own physical journey. From the object's own local perspective, its journey continues forward entirely normally, crossing the event horizon in what would feel like an unremarkable, continuous passage of time, exactly as described in our previous chapter. This raises a particular question worth pausing over, one that touches on something genuinely difficult to properly resolve, even among physicists who have spent entire careers studying precisely this kind of extreme gravitational physics. If time itself behaves so differently depending on one's particular gravitational circumstances, if a clock near a black hole's event horizon genuinely does tick at a dramatically different rate compared to a clock positioned safely farther away, what would the universe itself actually look like, experienced from a position deep within such an extreme gravitational field? This is not merely an abstract philosophical question, but one with genuine, concrete physical implications. An observer positioned very near a black hole's event horizon, were such a position somehow survivable, would witness the universe beyond unfolding at a dramatically accelerated pace relative to their own local experience of time. Events occurring far away, safely outside the black hole's most extreme gravitational influence, would appear from this hypothetical observer's perspective to unfold with startling speed, entire years, perhaps even centuries, of distant cosmic history seeming to pass in what felt locally like a comparatively brief stretch of time. This particular consequence of gravitational time dilation reveals something profound about the fundamental nature of time itself, a lesson worth carrying forward as our account continues. Time, we have discovered, is not some fixed, absolute backdrop against which the universe's events simply unfold, identical and unchanging regardless of circumstance. It is instead something considerably more fluid, considerably more intimately woven into the very same curved fabric of space that gravity itself represents a distortion within, a fabric capable of stretching, compressing, and varying its own local rate of passage, depending entirely on the particular gravitational conditions any given observer happens to occupy. Ahead of us lies a related, equally fascinating consequence of this same underlying physics, one concerning not merely how time itself behaves near a black hole, but how light, attempting its own impossible escape from the same extreme gravitational field, becomes bent, stretched, and ultimately trapped in ways that reveal something remarkable about the black hole's presence, even though the black hole itself remains, as always, entirely, permanently invisible. Throughout our journey so far, we have returned again and again to a single, central fact. A black hole itself cannot be seen directly, its event horizon marking a boundary beyond which no light can ever travel outward toward any observer, however powerful their instruments might be. And yet, paradoxically, black holes rank among the most extensively studied objects in all of modern astronomy, their existence confirmed not through any direct glimpse of the black hole itself, but through careful, patient observation of something considerably more accessible: the behavior of light passing nearby, light that never actually crosses the event horizon, but which nonetheless carries, within its own subtle distortions, unmistakable evidence of the black hole's presence. We touched briefly in an earlier chapter on the phenomenon of gravitational lensing, the bending of light around a massive object as it travels through the curved spacetime surrounding that object. It is worth now examining this effect considerably more closely, because it represents one of the most important tools available to astronomers hoping to study black holes indirectly, and because it reveals something genuinely beautiful about how light itself behaves under conditions of extreme gravitational curvature. Light under ordinary circumstances travels in perfectly straight lines, or at least what we would ordinarily describe as straight lines, through the otherwise uncurved geometry of empty space. But space, as we explored in earlier chapters, is not actually a fixed, unchanging backdrop. It is a fabric capable of being bent and warped by the presence of mass, and light, traveling through this same warped fabric, must necessarily follow whatever curved path that fabric happens to define, rather than continuing along the perfectly straight trajectory it would otherwise maintain through genuinely flat, uncurved space. Near an object as massive and as compact as a black hole, this curvature becomes extreme enough to bend light quite dramatically, producing visible, measurable distortions in the appearance of anything positioned behind the black hole from a given observer's particular vantage point. A star positioned directly behind a black hole relative to an observer's line of sight might have its light bent around the black hole from multiple different directions simultaneously, producing not a single point of light, but multiple distinct images of the very same star, each one having traveled along a slightly different curved path around the black hole's considerable gravitational influence. This effect grows increasingly extreme the closer light happens to pass to the black hole's event horizon, and it is precisely this increasing extremity that leads us toward a particularly fascinating concept, one that sits at a curious, genuinely fascinating boundary between light escaping entirely and light becoming permanently trapped. Consider light passing very close to a black hole, close enough that its path bends dramatically, but not quite close enough to cross the event horizon itself and become permanently trapped. At a certain very specific distance from the black hole center, distinct from the event horizon itself and situated slightly farther out, light can, under precisely the right conditions, enter into a stable circular orbit around the black hole, neither escaping outward nor falling inward, but instead circling the black hole indefinitely, trapped not beyond any hope of escape, but rather suspended in a kind of precarious, temporary balance. This particular region, where light itself can theoretically maintain a stable circular orbit around a black hole, is known as the photon sphere, and it represents one of the most genuinely strange consequences of extreme gravitational curvature anywhere in physics. It is worth noting immediately that this orbit, while theoretically stable in a mathematical sense, is also profoundly unstable in any practical sense. The slightest disturbance sufficient to send any orbiting photon either spiraling inward, ultimately crossing the event horizon and becoming permanently trapped, or else escaping outward, continuing its journey away from the black hole entirely. In practice, then, the photon sphere represents less a place where light actually settles into a permanent orbit, and more a critical threshold, a boundary marking the innermost possible distance at which light can approach a black hole and still have any chance whatsoever of continuing onward, rather than falling permanently inward across the event horizon itself. This photon sphere and the complex bending of light occurring in the region surrounding it together produce something that astronomers can, remarkably, actually observe and photograph directly, despite the black hole itself remaining permanently invisible, the black hole's shadow. This shadow represents the dark, roughly circular region created by the combined effect of the event horizon itself, from which no light can ever escape, and the surrounding photon sphere, where light approaching too closely becomes bent so severely that it, too, ultimately spirals inward rather than continuing on toward any distant observer. It is worth clarifying an important, easily overlooked distinction here, one that might otherwise create some confusion. The black hole's shadow, as observed and photographed by astronomers, is not, strictly speaking, identical to the event horizon itself. The shadow appears somewhat larger than the event horizon's actual physical boundary, a consequence of the additional light bending occurring within the surrounding photon sphere. Light that, while not having actually crossed the event horizon itself, still finds itself bent so severely that it never manages to reach any distant observer, contributing, in effect, to an apparent dark region somewhat larger than the true, underlying event horizon it surrounds. This distinction matters considerably, because it was precisely this shadow, rather than the event horizon itself, that astronomers finally managed to capture in the first-ever direct image of a black hole's immediate surroundings, an achievement we will explore in considerably greater detail in an upcoming chapter, once we have properly established the broader context surrounding the glowing, brilliant material that typically surrounds a black hole, providing the necessary backdrop of light against which this dark, otherwise invisible shadow finally becomes visible at all. For now, though, it is worth stepping back and appreciating something remarkable about everything we have covered across this particular chapter. Astronomers have never observed a black hole directly, not in the sense of ever detecting light originating from within the black hole itself. Every single observation ever made of a black hole, without exception, has relied instead on observing the behavior of light and matter in the black hole's immediate surroundings. Light bent and distorted by extreme gravitational curvature, matter disturbed in its orbital motion by an otherwise invisible gravitational influence, radiation emitted by material heated to extraordinary temperatures as it spirals inward toward an ultimate boundary from which it, too, will eventually be unable to return. This indirect approach to studying something fundamentally invisible represents one of the more remarkable achievements in the entire history of astronomy, a testament to just how much can genuinely be learned about an object through careful, patient study of its effects on everything surrounding it, even when the object itself remains, by its very nature, permanently beyond any possibility of direct observation. Every black hole ever confirmed to exist, from the relatively modest stellar mass black holes scattered throughout our own galaxy to the almost incomprehensibly massive black holes we will encounter later in our account, sitting at the very centers of entire galaxies, has been identified through precisely this kind of careful, indirect detective work, astronomers piecing together, from scattered clues of bent light and disturbed orbits, definitive evidence for objects that no telescope, however powerful, will ever manage to observe directly. Ahead of us lies a natural continuation of everything explored across this particular chapter, a closer examination of the glowing, extraordinarily energetic material that so often surrounds a black hole, spiraling ever closer to the event horizon before finally, inevitably, crossing that boundary and disappearing from view entirely. It is within this glowing material, rather than within the black hole itself, that some of the most brilliant, most visually spectacular phenomena in the entire universe actually take place. A striking, almost paradoxical contrast between absolute darkness at the very center of the scene and blazing, extraordinary brilliance immediately surrounding it. There is a particular kind of paradox worth sitting with as we turn now toward one of the most visually striking phenomena associated with black holes, a paradox that has, in various forms, threaded its way through nearly every chapter of our account so far, but which now becomes especially vivid and especially concrete. The darkest object in the entire universe, a region from which nothing, not even light, can ever escape, frequently finds itself surrounded by some of the brightest, most energetic material anywhere in the cosmos, blazing with such tremendous intensity that it can, under the right circumstances, outshine entire galaxies of ordinary stars. This glowing material encircling a black hole in a wide, flattened, spiraling structure is known as an accretion disk, and understanding how it forms and why it grows so extraordinarily bright requires us to think carefully about what actually happens to matter as it falls toward a black hole, rather than assuming, as popular imagination sometimes does, that anything nearby simply vanishes directly and immediately into the darkness. Matter falling toward a black hole rarely falls in a simple, direct straight line, plunging immediately toward the event horizon along the shortest possible path. Instead, much like planets orbiting a star, matter approaching a black hole typically possesses some degree of angular momentum, some rotational motion around the black hole's center, inherited from whatever process originally set that matter moving in the first place, whether it be gas drawn from a companion star or material scattered throughout the surrounding environment of a galaxy's crowded central region. This rotational motion means that matter cannot simply fall directly inward. It must instead spiral gradually toward the black hole, tracing an increasingly tight, increasingly rapid orbit, gradually losing altitude, so to speak, much as water circling a drain spirals inward gradually rather than falling immediately and directly through the center. As this matter spirals inward, drawn together into an increasingly dense, increasingly crowded orbital structure, something significant begins to happen, a direct consequence of countless individual particles, all moving along slightly different orbital paths, inevitably colliding and rubbing against one another with tremendous, ever-increasing frequency. This friction, generated by matter within the accretion disk colliding and interacting as it spirals inward, converts a considerable portion of that matter's orbital energy directly into heat, and not merely a modest amount of heat, but heat reaching truly extraordinary temperatures, particularly within the innermost regions of the disk, closest to the black hole itself, where matter moves fastest and collisions occur most violently and most frequently. Temperatures within the innermost portions of an accretion disk can reach into the millions of degrees, conditions extreme enough that the material involved no longer behaves as an ordinary gas at all, but instead as plasma, an extraordinarily energetic state of matter in which atoms have been stripped of their electrons entirely, the resulting charged particles interacting through powerful electromagnetic forces, in addition to the more straightforward gravitational forces already at work. Material heated to these extraordinary temperatures emits radiation across an enormous range of wavelengths, including considerable quantities of X-rays and other high-energy radiation entirely invisible to the human eye, but readily detectable by specialized space-based telescopes specifically designed to observe precisely this kind of extreme, high-energy emission. It is this glowing, superheated material, rather than the black hole itself, that accounts for the tremendous brightness so often associated with black holes throughout popular imagination, and indeed throughout genuine scientific observation as well. When we speak of a particularly bright, particularly energetic black hole system, we are, in every case, actually describing the brightness of this surrounding accretion disk, not any light originating from the black hole itself, which, as we have established repeatedly throughout this account, remains permanently, absolutely dark, incapable of emitting any light whatsoever from within its own event horizon. This accretion disk, brilliant and extraordinarily energetic as it becomes, also exhibits several additional, genuinely fascinating effects directly connected to the extreme physics we have explored across earlier chapters, effects that further distinguish the light emerging from very near a black hole from ordinary light emitted under more conventional circumstances elsewhere in the universe. Material on the side of the accretion disk rotating toward a distant observer, for instance, moves at such extraordinary speed, in certain cases approaching a meaningful fraction of the speed of light itself, that its emitted light becomes measurably shifted toward higher frequencies, an effect known as Doppler shifting, closely related to the more familiar acoustic version of the same phenomenon, in which an ambulance siren appears to rise in pitch as it approaches and fall in pitch as it recedes. Material on the opposite side of the disk, rotating away from the same observer, exhibits precisely the opposite effect, its light shifted toward lower frequencies instead. Beyond this Doppler shifting, light emerging from deep within an accretion disk's most extreme gravitational environment also experiences gravitational redshift, a phenomenon directly related to the gravitational time dilation explored in our previous chapters. Light climbing outward from a region of intense gravitational curvature loses a portion of its energy in the process, an effect that manifests as a measurable shift toward longer, redder wavelengths, becoming increasingly pronounced the closer to the event horizon that light originally happened to be emitted. Together, these combined effects, extraordinary heat generated through friction, Doppler shifting arising from tremendous orbital speeds, and gravitational redshift arising from extreme spacetime curvature, produce an accretion disk considerably more complex and considerably more scientifically revealing than a simple, uniformly glowing ring might otherwise suggest. Careful analysis of precisely how light from different portions of an accretion disk has been shifted and distorted allows astronomers to extract remarkably detailed information about the black hole at its center, including its mass, its rate of rotation, and even in certain particularly well-studied cases, considerable detail about the precise geometry of the surrounding spacetime itself, information gathered entirely indirectly, without ever observing the black hole directly. Exactly as described throughout our previous chapter. There is something worth pausing on here, a particular kind of visual and conceptual beauty that emerges from everything we have described across this chapter, one worth holding in mind as we continue our broader account. Picture, if you will, this entire scene as it might actually appear, were it somehow possible to observe safely from a suitable distance. A perfectly dark circular void at the very center, surrounded immediately by a brilliant, blazing ring of superheated matter, spiraling inward with tremendous speed, glowing with such intensity across such an enormous range of wavelengths that the entire structure can, under the right circumstances, outshine every ordinary star within its host galaxy combined. It is a scene of extraordinary contrast, absolute darkness bordered immediately by absolute brilliance, each existing only because of the other, the darkness created by gravity strong enough to trap light entirely, the brilliance created by matter's own desperate, ultimately futile struggle against that same overwhelming gravitational pull. This particular paradox, an object defined by its absolute darkness existing at the very heart of one of the universe's brightest possible environments, captures something essential about black holes more broadly, a theme we will continue to encounter throughout the remainder of our account. Black holes themselves remain forever silent, forever invisible, forever beyond any possibility of direct observation. And yet, everywhere they exist, they leave behind unmistakable, often spectacular evidence of their presence, evidence written not within the darkness itself, but within everything that darkness inevitably, dramatically affects. Ahead of us lies a natural continuation of the same theme, one exploring how certain black hole systems manage to convert the same accretion disk, and the extraordinary energy it generates, into something even more visually dramatic still, launching enormous jets of matter outward across distances vast enough to span entire galaxies, transforming what began as a simple, invisible gravitational anomaly into something closer to a genuine cosmic lighthouse, visible, under the right circumstances, from clear across the observable universe. There exists around certain black holes a phenomenon that seems, at least at first glance, to contradict everything we have carefully established across the preceding chapters of this account. We have spoken repeatedly, and with considerable emphasis, about black holes as objects defined fundamentally by what they trap, by what they pull inexorably inward, never to return. And yet, around certain particularly active black holes, astronomers have observed something that appears on its surface to represent precisely the opposite. Enormous jets of matter, launched outward from the immediate vicinity of the black hole itself, traveling at speeds approaching a significant fraction of the speed of light, extending outward across distances so vast that they can, in certain extreme cases, span distances greater than the host galaxy containing the black hole in the first place. This apparent contradiction deserves careful, honest examination, because resolving it reveals something genuinely important about black holes more broadly, correcting a particular misconception that persists, quite understandably, throughout much of popular imagination. Black holes, despite their popular reputation, do not actually behave as cosmic vacuum cleaners, indiscriminately drawing in and consuming everything within some broad surrounding region of space. A black hole's gravitational influence, beyond a certain distance, behaves exactly as any other object of equivalent mass would behave, no more and no less. Earth, for instance, would continue orbiting our Sun in an entirely unchanged, stable orbit, even if the Sun were somehow instantaneously replaced by a black hole of precisely equal mass, so long as Earth remained at its current orbital distance. The popular image of a black hole relentlessly, actively hunting down and consuming everything within its surroundings, simply does not reflect the actual underlying physics involved. What a black hole does possess, however, particularly when actively accreting matter through the kind of glowing disk explored in our previous chapter, is an extraordinarily powerful, extraordinarily complex magnetic environment, one capable of interacting with the superheated electrically charged plasma spiraling within its accretion disk in ways that can ultimately launch a portion of that same material outward, rather than allowing it to continue its inward spiral toward the event horizon. To understand how this outward launching actually occurs, it helps to recall that the material within an accretion disk exists in the form of plasma, matter so extraordinarily hot that its atoms have been stripped entirely of their electrons, leaving behind a swirling mixture of charged particles rather than ordinary, electrically neutral gas. Charged particles moving through space generate magnetic fields, and the combined motion of countless charged particles within an accretion disk can generate magnetic fields of tremendous overall strength, fields that become twisted and wound tightly together by the disk's own rapid rotational motion, not unlike the way repeatedly twisting a rubber band causes it to coil ever more tightly upon itself. These twisted, tightly wound magnetic fields, anchored within the rotating accretion disk itself, can extend outward along the black hole's rotational axis, the imaginary line running directly through its center, perpendicular to the disk's own rotational plane. Along this particular axis, the combined effect of these powerful magnetic fields, working in conjunction with the black hole's own considerable rotational energy, can accelerate a portion of the surrounding charged plasma to tremendous speed, flinging this material outward along two narrow, tightly focused beams, one extending from each pole of the black hole's rotational axis, rather than allowing this particular portion of the surrounding material to continue its inward spiral toward the event horizon. These narrow, high-speed beams of ejected plasma are known as relativistic jets, a name reflecting the fact that the material within them typically travels at speeds close enough to the speed of light that the effects of Einstein's theory of relativity become significant in describing their behavior. These jets can extend outward across truly staggering distances, in certain particularly dramatic cases stretching for hundreds of thousands or even millions of light years, distances vastly exceeding the size of the host galaxy from which they originate, carrying material and energy far out into the largely empty space beyond. It is worth pausing here to properly appreciate the genuine strangeness and the genuine elegance of what we have just described. The very same black hole responsible for trapping light so completely that nothing can ever escape once it crosses the event horizon is also, indirectly, responsible for launching some of the most energetic, most far-reaching structures anywhere in the observable universe. This is not, it is worth emphasizing clearly, a contradiction of anything established in earlier chapters. The jets themselves never actually originate from within the event horizon, nor from anywhere close to it. They are launched from the surrounding accretion disk and the black hole's powerful, extended magnetic field, material that never actually crossed the point of no return in the first place, redirected outward before ever reaching that final, irreversible boundary. This phenomenon becomes particularly significant and particularly dramatic when it occurs around the truly enormous black holes that reside at the very centers of galaxies, objects we will examine in considerably greater detail in our next chapter, but which deserve brief introduction here in order to properly understand the full scale of what these jets are actually capable of producing. When a supermassive black hole, sitting at a galaxy center, actively accretes surrounding matter and launches jets in the manner just described, the entire surrounding region can become extraordinarily luminous, producing what astronomers refer to as an active galactic nucleus, a compact, extraordinarily bright region at the very heart of an otherwise ordinary galaxy, sometimes bright enough to outshine every single star within that galaxy combined. Despite originating from a region of space no larger, in relative terms, than our own solar system. Among the most extreme examples of this phenomenon are objects known as quasars, among the most luminous, most energetic objects known to exist anywhere in the entire universe, many of them observed at such tremendous distances that the light reaching our telescopes today began its own journey billions of years ago, offering astronomers a genuine window into the conditions present throughout the early universe, not long after galaxies themselves first began to properly form. A quasar's extraordinary brightness stems entirely from precisely the mechanism described throughout this chapter, an actively accreting supermassive black hole, its surrounding disk heated to extraordinary temperatures, its powerful magnetic fields launching relativistic jets outward across distances almost impossible to properly comprehend. There's a particular image worth holding onto as we bring this chapter toward its close, one that captures something genuinely remarkable about the broader relationship between black holes and light, a relationship considerably more complex and considerably more paradoxical than the simple, popular image of an all-consuming cosmic void might otherwise suggest. A black hole, an object defined by its absolute inability to emit any light whatsoever from within its own boundary, can nonetheless become, indirectly, the very engine driving some of the brightest, most far-reaching beacons anywhere in the observable universe, transforming the ordinary matter unfortunate enough to fall within its gravitational influence into jets of light and energy capable of illuminating distances spanning entire galaxies, and of carrying information about their source across distances so vast that this same light continues arriving at our own telescopes today, having traveled for literally billions of years to finally reach us, a genuine cosmic lighthouse, its beam cast outward not despite the black hole's own perfect darkness, but directly because of it. Ahead of us lies a natural expansion of everything explored across this particular chapter, a shift in scale from the individual black holes we have examined so far, remnants of massive dying stars, towards something considerably larger, considerably stranger, and considerably more consequential to the broader structure of galaxies themselves. The truly enormous, supermassive black holes that reside, as far as astronomers can currently determine, at the very center of nearly every major galaxy throughout the observable universe, including, quite remarkably, our own. Everything we have explored so far regarding black holes, their formation from the collapsed cores of massive dying stars, their accretion disks, their relativistic jets, has concerned what astronomers refer to as stellar mass black holes, objects typically possessing a mass somewhere between a few times and perhaps a few dozen times that of our own sun, entirely consistent with their origin as the collapsed remnants of individual massive stars. But black holes, it turns out, do not stop at this particular scale. Scattered throughout the universe exist objects that dwarf even the most massive stellar black holes by a truly staggering margin, black holes possessing masses not merely a few dozen times that of our sun, but millions, and in certain extreme cases, billions of times greater still. These extraordinary objects are known as supermassive black holes, and their existence raises a question worth sitting with immediately before we proceed any further. How does a black hole come to possess a mass millions or billions of times greater than our own sun, when the collapse of even the most massive individual star, as described in our earlier chapters, produces a black hole only a relatively modest number of times more massive than the sun itself? This question touches on one of the genuine, still not entirely resolved mysteries surrounding supermassive black holes, one we will return to directly before this chapter concludes. But first, it is worth properly establishing exactly what these objects are and precisely where they tend to be found. Remarkably, current astronomical evidence strongly suggests that nearly every sufficiently large galaxy throughout the observable universe, our own included, harbors a supermassive black hole at its very center, a single, extraordinarily massive object sitting at the gravitational heart of hundreds of billions of ordinary stars, all orbiting this central point across timescales stretching into the hundreds of millions of years. This is not merely theoretical speculation. Astronomers have gathered considerable direct evidence for precisely this kind of central supermassive black hole within our own Milky Way galaxy, evidence gathered through one of the most patient, most carefully executed observational projects in the entire history of astronomy. At the very center of our own galaxy resides an object astronomers call Sagittarius A*, a name derived from its position within the constellation Sagittarius as observed from Earth, combined with a designation reflecting its status as an unusually bright source of radio emissions. For several decades, astronomers have carefully tracked the motion of stars orbiting extremely close to this particular location, stars moving at extraordinary speeds along tight, rapid orbits entirely unlike anything observed elsewhere within our galaxy's more ordinary outer regions. By carefully measuring the precise orbital paths of these stars, tracking their positions with tremendous precision across years and even decades of patient, continuous observation, astronomers were able to calculate, with considerable confidence, the mass of whatever invisible object these stars were actually orbiting. The result, confirmed through multiple independent lines of evidence gathered by different research teams using different instruments and different methodologies, revealed something extraordinary. An object with a mass roughly 4 million times that of our own Sun, concentrated within a region of space remarkably small given this enormous mass, entirely consistent with the properties expected of a supermassive black hole, despite the fact that Sagittarius A itself, exactly as we would expect given everything established throughout this account, remains permanently invisible, its presence confirmed entirely through its powerful, unmistakable gravitational influence on the surrounding stars. This method, tracking the orbital motion of stars or surrounding gas in order to infer the presence and mass of an otherwise invisible central object, represents the primary technique astronomers have used to confirm the existence of supermassive black holes at the centers of countless other galaxies as well, extending our confidence in these objects' existence considerably beyond just our own particular corner of the universe. Nearly every sufficiently massive galaxy studied in adequate detail has revealed evidence of precisely this kind of central supermassive object, ranging from a few million solar masses in relatively modest galaxies like our own, to several billion solar masses in certain, particularly enormous galaxies observed elsewhere throughout the universe. This near-universal presence of supermassive black holes at galactic centers has led astronomers toward a particularly intriguing area of ongoing research, one concerning the relationship between a galaxy and its own central black hole. It might seem, given the enormous disparity in scale between an individual black hole and an entire galaxy's worth of hundreds of billions of stars, that any influence a central black hole exerts on its host galaxy would remain relatively negligible, confined largely to the immediate region surrounding the black hole itself. And yet considerable evidence suggests something rather more significant, a genuine ongoing relationship between a galaxy's overall properties and the particular characteristics of its central black hole, including a notable correlation between a black hole's mass and various broader properties of its host galaxy, a correlation that would seem quite unlikely to exist purely by coincidence, given the vast disparity in scale involved. The precise mechanisms underlying this relationship remain an area of active, ongoing scientific investigation. But one particularly compelling possibility involves the same relativistic jets and intense radiation explored in our previous chapter, energy capable under the right circumstances of heating and dispersing gas throughout an entire host galaxy, potentially influencing, in ways still being carefully studied, the broader galaxy's own ongoing formation of new stars. A supermassive black hole, in other words, may not simply exist as a passive, gravitationally dominant object sitting quietly at a galaxy center, but may instead play an active, ongoing role in shaping the very galaxy that surrounds it, an idea that continues to reshape astronomers' broader understanding of how galaxies themselves form and evolve across cosmic time. This brings us back finally to the genuine mystery we set aside at the beginning of this chapter, the question of precisely how these enormous objects came to exist in the first place. We understand with considerable confidence how stellar mass black holes form through the dramatic collapse of a single massive star's core, exactly as described in our earlier chapters. But this mechanism alone cannot easily account for objects millions or billions of times more massive still, particularly given that astronomers have observed evidence of fully formed supermassive black holes existing remarkably early in the universe's overall history, at a stage when there would have been comparatively little time available for a black hole to grow to such an enormous size through the relatively gradual, incremental process of continuously accreting surrounding matter over many billions of years. This apparent timing problem represents one of the genuine, still actively debated mysteries within modern astrophysics. Several possible explanations have been proposed, including the possibility that certain unusually massive stars within the early universe, considerably larger than any stars typically observed today, may have collapsed directly into black holes of already substantial mass, providing something closer to a considerable head start compared to the relatively modest stellar mass black holes we typically observe forming in the more recent universe. Other researchers have proposed alternative mechanisms entirely, involving the direct, rapid collapse of enormous, unusually dense clouds of primordial gas, bypassing the star formation process altogether and producing an already substantial black hole considerably more quickly than the conventional stellar collapse mechanism would otherwise allow. It is worth acknowledging directly, with the same honesty this account has maintained throughout, that this particular question, precisely how supermassive black holes manage to grow so enormous so quickly within the universe's own relatively early history, remains genuinely unresolved, an active area of ongoing research rather than a settled, well-understood matter. This uncertainty should not be taken as any kind of weakness in our broader understanding of black holes generally, but rather as an honest acknowledgement that even a subject studied as extensively as black holes continues to hold genuine mysteries, questions that current evidence has not yet fully managed to resolve. There is something worth pausing on here, a genuine sense of scale worth properly appreciating before we continue further into our account. We began this particular exploration of black holes with objects formed from the collapse of a single massive star, remnants typically possessing a mass only a modest multiple of our own sun's considerable mass. We arrive now at objects millions, even billions of times more massive still, sitting quietly at the very center of entire galaxies, their gravitational influence extending outward across distances vast enough to shape the orbital motion of stars scattered throughout their host galaxies' entire central region. This is the genuine range of scale black holes are capable of occupying, from the relatively modest remnants of individual stellar deaths, to objects so overwhelmingly massive that they may play a fundamental, ongoing role in shaping the very galaxies that surround them. Ahead of us lies a return to a considerably more intimate scale, though no less dramatic for it, as we turn our attention toward what happens when two black holes, rather than existing in relative isolation, find themselves drawn together across cosmic time, locked into a slow, inevitable gravitational dance that will eventually culminate in one of the most violent, most energetic events the universe is capable of producing. Throughout our account so far, we have generally considered black holes as solitary objects, each one existing in relative isolation, its gravitational influence extending outward into the surrounding darkness, affecting nearby matter and light, but otherwise proceeding through its own quiet, undisturbed existence. This picture, while accurate for a great many black holes scattered throughout the universe, does not capture the full range of what black holes are actually capable of experiencing. In certain cases, two black holes find themselves gravitationally bound to one another, orbiting a shared center of mass in what astronomers call a binary system, a configuration that sets the stage for one of the most extraordinary, most energetic events the universe is capable of producing. Binary black hole systems typically originate from binary star systems, two massive stars that form together, orbiting one another throughout their entire, considerable lifetimes, before each, in turn, eventually exhausted its own nuclear fuel and collapsed, following precisely the process described in our second chapter, into a black hole of its own. Rather than separating following this dramatic transformation, these two black holes, if their original orbital configuration remained sufficiently stable throughout this entire process, continue orbiting one another, now as two black holes rather than two stars, locked together in a gravitational dance that will, given sufficient time, eventually draw them into a truly extraordinary encounter. This ongoing orbital relationship, seemingly stable across any reasonably short observation, actually conceals a slow, gradual, but entirely inevitable process of decay, one directly connected to a phenomenon we touched upon only briefly in earlier chapters, but which now deserves considerably more careful examination: gravitational waves. According to Einstein's general theory of relativity, any sufficiently massive object undergoing acceleration, and two black holes locked in mutual orbit are indeed constantly accelerating, continuously changing direction as they circle one another, will generate ripples in the very fabric of spacetime itself, ripples that propagate outward from their source at the speed of light, carrying away in the process a small but genuinely real quantity of energy from the orbiting system that originally produced them. This continuous, ongoing loss of energy, radiated away gradually in the form of gravitational waves, has a direct, measurable consequence for the orbiting black holes themselves. As the system loses energy, the two black holes' mutual orbit gradually shrinks, drawing them incrementally closer together with each passing orbit, a process that, for the vast majority of a binary black hole system's existence, proceeds with such extraordinary slowness that it remains entirely undetectable across any reasonable span of human observation, the two black holes appearing, for all practical purposes, to maintain an essentially unchanging, stable orbital relationship across many thousands or even millions of years. But this gradual shrinking, however slow it may initially proceed, does not continue indefinitely at the same measured pace. As the two black holes draw closer together, their mutual gravitational influence on one another grows correspondingly stronger, causing them to orbit one another with increasing speed, which in turn causes the system to radiate gravitational waves with increasing intensity, which in turn causes the orbit to shrink at an increasingly rapid rate. This creates a kind of runaway process, slow and almost imperceptible across the vast majority of the system's existence, but accelerating dramatically and increasingly rapidly as the two black holes approach their final, inevitable encounter. In the final moments before this ultimate encounter, moments that remarkably unfold across mere fractions of a second following what may have been many millions or even billions of years of gradual, almost imperceptible orbital decay, the two black holes begin orbiting one another at speeds approaching a significant fraction of the speed of light itself, their mutual orbit shrinking with such extraordinary rapidity that what had, for the vast majority of the system's existence, been an almost static, unchanging configuration transforms, within these final fleeting moments, into one of the most violent, most rapidly evolving events the universe is capable of producing. Finally, in a moment of genuine, almost unimaginable cosmic violence, the two black holes merge entirely, their individual event horizons combining into a single, larger event horizon, two previously separate, previously invisible objects becoming, in an instant, one considerably larger black hole, its final mass somewhat less than the simple combined total of the two original black holes, the difference having been radiated outward across the course of this entire merger process, in the form of gravitational waves carrying away an amount of energy almost impossible to properly convey through ordinary language, in certain particularly dramatic mergers exceeding, for a brief fraction of a second, the combined light output of every single star within the entire observable universe, radiated not as light at all, but entirely as ripples within the fabric of spacetime itself. There is something worth pausing on here, something genuinely remarkable about the nature of this particular event, one that connects directly back to the central paradox introduced at the very beginning of our account. Two black holes, each individually defined by its own complete absolute silence, each incapable of producing any light or sound whatsoever from within its own event horizon, can nonetheless collide in an event so energetic, so violent, that it briefly outshines, in terms of pure energy output, every ordinary star throughout the entire observable universe combined, an event witnessed not through any telescope capable of detecting light, but through an entirely different kind of instrument altogether, one designed specifically to detect the passage of gravitational waves themselves, rippling outward through spacetime from a collision that occurred, in many confirmed cases, over 1 billion years before that same signal finally arrived, faintly but unmistakably, at Earth's own specially designed detectors. This particular achievement, the first direct detection of gravitational waves produced by precisely this kind of black hole merger, represents one of the genuine landmark achievements in the entire history of astronomy, a moment we will examine in considerably greater detail in our next chapter, exploring both the extraordinary technical achievement required to actually detect these incredibly faint ripples in spacetime, and the profound new window this detection opened onto an entire category of cosmic events that had, until remarkably recently, remained entirely invisible to every previous method of astronomical observation ever developed. For now, though, it is worth simply sitting with the scene itself, allowing its full scale and its full strangeness to properly register. Two invisible, silent objects, each having formed through the dramatic, violent death of a massive star, drawn together gradually across a span of time potentially reaching into the billions of years, locked in an increasingly rapid, increasingly violent gravitational dance, culminating finally in a merger of such extraordinary energy that it briefly reshapes the very fabric of spacetime itself, sending ripples outward across the universe that will, eventually, many years or many millions of years later, depending on the particular merger in question, reach some distant observer capable of detecting them, offering in that single fleeting moment of detection unmistakable evidence of a cosmic collision that occurred long before that detection ever became possible, between two objects that neither light nor sound could ever have revealed on their own. It is to this remarkable detection itself, and to the broader, genuinely revolutionary science of gravitational wave astronomy it helped establish, that our account now turns. We have spoken, across the previous chapter, of gravitational waves in relatively abstract terms, ripples in the very fabric of spacetime itself, generated by the extraordinary violence of two black holes spiraling together and finally merging into one. It is worth now pausing to properly understand exactly what these waves actually are, how they were finally detected after decades of patient scientific effort, and why astronomers have come to describe this entire field of study using a particular, evocative phrase: learning, for the first time in human history, to listen to the universe rather than simply observing it. To understand what a gravitational wave actually is, it helps to return once more to Einstein's fundamental insight regarding the nature of space and time, the same insight that has guided nearly every chapter of our account so far. Space and time, according to general relativity, do not form a fixed, unchanging backdrop against which the universe's events simply unfold. They form instead a single, dynamic, interconnected fabric, one capable of being bent and curved by the presence of mass, and crucially, one capable of actually rippling, stretching, and compressing in a genuine physical wave whenever sufficiently massive objects undergo sufficiently violent acceleration. A gravitational wave, then, is not a wave traveling through space, in the way an ordinary sound wave travels through air, or an ordinary light wave travels through the vacuum of space itself. It is rather a wave within space, a genuine physical distortion of space's own underlying geometry, stretching space very slightly in one direction while simultaneously compressing it very slightly in the perpendicular direction, before reversing the same pattern as the wave continues propagating outward, a rhythmic, oscillating distortion traveling outward from its source at the speed of light itself, exactly as Einstein's original equations predicted more than a century ago. It is worth being entirely clear about just how extraordinarily faint these waves become by the time they reach any distant observer, because this faintness explains why gravitational waves, despite being predicted with considerable theoretical confidence for the better part of a century, remained entirely undetected until remarkably recently. A gravitational wave produced by an event as violent as a black hole merger, having traveled across a distance of perhaps 1 billion light-years before finally reaching Earth, produces a distortion in space itself so extraordinarily small that detecting it required an instrument capable of measuring a change in distance smaller than 1/10,000th the width of a single proton, across a detector spanning several kilometers in overall length. An almost unimaginable feat of precision engineering that took decades of dedicated scientific and technical effort to finally achieve. This achievement finally arrived in September of 2015, when the Laser Interferometer Gravitational Wave Observatory, generally known by its acronym LIGO, successfully detected, for the very first time in human history, a genuine gravitational wave signal, one that careful subsequent analysis confirmed had been produced by precisely the kind of black hole merger described throughout our previous chapter, two black holes. Each possessing a mass several dozen times that of our own Sun, having spiraled together and merged at a distance of well over 1 billion light-years from Earth, the resulting ripple in spacetime having traveled, uninterrupted, across this entire vast distance before finally arriving, faintly but unmistakably, at LIGO's own extraordinarily sensitive detectors. LIGO's detection method involves a technique known as laser interferometry, in which a highly precise laser beam is split into two separate beams, each traveling down one of two long, perpendicular tunnels, several kilometers in length, before being reflected back and recombined at their original starting point. Under ordinary, undisturbed conditions, these two beams recombine in a precisely predictable way, having traveled identical distances down their respective perpendicular tunnels. But if a gravitational wave happens to pass through the detector at precisely the right moment, very slightly stretching one tunnel while very slightly compressing the other, the two beams will have traveled very slightly different distances, producing a correspondingly tiny, but genuinely measurable, shift in how they recombine. A shift so extraordinarily small that only the most sophisticated, most carefully isolated instruments ever constructed have proven capable of reliably detecting it. It is worth pausing here to appreciate something particularly evocative about how scientists studying gravitational waves have chosen to describe their own data, because it connects directly to the broader theme running throughout this entire chapter. The particular pattern of distortion produced by a black hole merger, when converted from its original form as a measurement of spacetime distortion into an ordinary audio waveform, produces something remarkably close to an audible sound, a brief, rising tone often described as a distinctive chirp, rising rapidly in both pitch and intensity as the two merging black holes spiral together with increasing speed, before ending abruptly at the precise moment of their final merger. Scientists studying these signals frequently do, in fact, convert their gravitational wave data directly into audible sound, allowing researchers and members of the public alike to genuinely listen to the actual signature of a black hole merger occurring over 1 billion years ago, translated from a pattern of spacetime distortion into a brief, distinctive sound perceptible to human ears. This practice, converting gravitational wave data into audible sound, reflects something genuinely significant about what this entire field of study actually represents, beyond merely offering an evocative, accessible way of communicating scientific results to a broader audience. For the entire previous history of astronomy, stretching back across many centuries of careful observation, virtually every method available for studying the universe relied, in one way or another, on detecting light, whether the visible light our own eyes can directly perceive, or the broader range of electromagnetic radiation, radio waves, X-rays, infrared, and ultraviolet light, that our instruments have gradually learned to detect and interpret across the past century or so of scientific progress. Gravitational waves represent something categorically different, an entirely separate channel of information about the universe, one that does not rely on light or any other form of electromagnetic radiation whatsoever, but instead on the direct physical distortion of spacetime itself. This distinction carries genuine, significant scientific consequences. Certain cosmic events, including black hole mergers precisely like the one first detected by LIGO in 2015, produce gravitational waves without necessarily producing any significant quantity of light at all. Given that black holes themselves, as established throughout this entire account, remain permanently incapable of emitting light directly. Prior to LIGO's landmark detection, such events would have remained entirely invisible to every previous method of astronomical observation ever developed, their occurrence forever unknown and undetectable, regardless of how powerful or how sophisticated our light-based telescopes might eventually become. Gravitational wave astronomy, in this sense, does not merely represent an incremental improvement over previous observational techniques. It represents an entirely new sense, a genuinely new way of perceiving the universe, one capable of detecting events that would otherwise have remained forever silent, forever invisible, and forever unknown. Since LIGO's initial landmark detection in 2015, astronomers have gone on to detect numerous additional gravitational wave signals, confirming not only additional black hole mergers, but also, in certain particularly significant cases, collisions between neutron stars as well, events that, unlike black hole mergers, do produce significant quantities of ordinary light alongside their gravitational wave signature, allowing astronomers, for the first time, to observe the very same cosmic event through two entirely independent channels simultaneously, comparing and cross-referencing gravitational wave data with more conventional light-based observations, in a genuinely new, genuinely powerful approach to astronomy that researchers have come to call multi-messenger astronomy. Looking ahead, astronomers continue working to construct increasingly sensitive gravitational wave observatories, including proposed space-based detectors capable of detecting gravitational waves at frequencies entirely inaccessible to ground-based instruments like LIGO, potentially opening an even wider window onto categories of cosmic events that remain, even now, entirely undetected by any currently existing instrument. There is a particular thought worth carrying forward as we bring this chapter toward its close, one that returns us directly to the central paradox first introduced at the very beginning of our entire account. Black holes, we have said repeatedly, exist in complete, total silence, incapable of producing any sound or light whatsoever through any conventional means. And yet, when two such silent, invisible objects finally collide, the resulting event can leave behind a detectable rhythm rippling outward through the very fabric of spacetime itself. A genuine signal capable of being converted, quite literally, into sound that any sufficiently sensitive instrument, positioned billions of light years away, might eventually detect and interpret as unmistakable evidence of a violent, silent collision that occurred long before that detection ever became possible at all. Ahead of us lies a return to a question we have, until this point, largely set aside, one concerning not what happens around a black hole, but what happens within it, beyond the event horizon itself, in the one region of the universe that no telescope and no gravitational wave detector will ever be capable of directly observing. Throughout this entire account, we have carefully, deliberately confined ourselves to what can actually be observed, directly or indirectly, about black holes. Their formation from the collapsed cores of massive dying stars, the light bent and distorted in their immediate surroundings, the glowing accretion disks and relativistic jets that betray their otherwise invisible presence, the gravitational waves rippling outward from their most violent collisions. Every single piece of evidence explored so far has concerned what happens outside a black hole's event horizon, in the region of the universe that remains, at least in principle, accessible to careful scientific observation. We turn now, finally, toward the single question this entire account has been building toward from its very first chapter, a question considerably more difficult to answer with any genuine confidence. What actually happens after crossing the event horizon itself? It is worth being entirely honest, from the very outset of this particular chapter, about the genuine limits of what we can actually claim to know here. Every observation described throughout this account, without exception, has relied on information that ultimately reached us from outside a black hole's event horizon, light bent by its gravity, Matter disturbed in its orbit, gravitational waves radiated outward before any final merger. Nothing, by definition, can ever travel outward from within the event horizon itself, which means no observation, however sophisticated, however patient, will ever directly confirm what actually occurs within this forbidden region. Everything we are about to discuss, then, rests not on direct observation, but on mathematics, on the careful, rigorous extension of Einstein's equations into a region where, as we will see, those very equations may ultimately reach the limits of their own reliability. According to the mathematics of classical general relativity, extended all the way to its ultimate, most extreme conclusion, the fate of matter falling within a black hole's event horizon is startling in its apparent simplicity. Every possible path available to that matter, as established in our earlier chapter on the event horizon itself, leads inevitably inward toward the black hole's exact center. And at that exact center, according to these same equations, extended to their absolute mathematical limit, all of that matter becomes compressed into a single point of literally infinite density, a region of space with, quite genuinely, zero volume, containing within it the entire mass that originally collapsed to form the black hole in the first place. This theoretical point is known as a singularity, and it represents, at least according to the straightforward mathematics of general relativity taken entirely at face value, the ultimate fate awaiting anything and everything that ever crosses a black hole's event horizon. It is worth pausing here and pausing carefully because this particular concept, an actual point of genuinely infinite density, deserves considerably more careful scrutiny than simply accepting it as a straightforward, literal description of physical reality. Infinities within physics more broadly tend to serve as a particular kind of warning sign, a signal that a given theory, however successful and however well tested within its own proper domain, has likely been extended beyond the actual boundaries of its genuine reliability. This is not merely a matter of philosophical unease with the concept of infinity itself. It reflects a considerably more concrete, considerably more specific scientific concern, one worth examining directly. General relativity, the theory responsible for nearly everything we have explored throughout this entire account, curved spacetime, gravitational time dilation, the bending of light, gravitational waves themselves, represents one of the most thoroughly tested, most consistently successful theories in the entire history of physics. Its predictions confirmed across more than a century of increasingly precise experimental and observational scrutiny. But general relativity is not, and was never intended to be, a complete description of every aspect of physical reality. It describes with extraordinary precision how mass and energy curve the geometry of space and time across relatively large scales, the scale of planets, stars, galaxies, and the universe as a whole. It says considerably less, however, about the behavior of matter and energy at the extraordinarily small scales where an entirely different branch of physics, quantum mechanics, takes over as the dominant, most accurate framework available. Quantum mechanics, developed largely alongside general relativity throughout the early 20th century, describes the behavior of matter and energy at the smallest possible scales, the realm of individual atoms and subatomic particles, and it has proven every bit as successful, every bit as thoroughly confirmed through careful experimentation, as general relativity itself, within its own particular domain of applicability. The genuine, ongoing difficulty within modern physics lies in the fact that these two extraordinarily successful theories, general relativity and quantum mechanics, have never been fully, satisfactorily unified into a single, coherent framework capable of accurately describing situations where both extremely strong gravity and extremely small scales become simultaneously relevant, precisely the conditions that would actually prevail at a black hole's genuine central singularity. Where an entire star's worth of mass has, according to general relativity's own equations, been compressed into a region of literally zero volume. This is precisely why many physicists suspect, with considerable justification, that the singularity predicted by classical general relativity likely does not represent an accurate, literal description of what actually exists at a black hole's center, but rather represents a signal that general relativity, however successful it remains across nearly every other context we have explored throughout this account, has simply been pushed here into a regime. Extraordinarily strong gravity operating across extraordinarily small distances, where its own equations are no longer capable of providing a reliable, accurate description of physical reality. A regime where the still undiscovered effects of quantum gravity, a fully unified theory combining general relativity and quantum mechanics that physicists have yet to successfully develop, would presumably become dominant, potentially replacing the singularity's mathematically troublesome infinite density with something rather different, some genuinely finite, if still extraordinarily extreme, physical configuration that current physics remains simply unable to properly describe or predict. It is worth emphasizing, with the same honesty maintained throughout this entire account, that this remains, even now, one of the most significant, most actively pursued open questions in all of modern theoretical physics. Numerous different approaches toward developing a genuine theory of quantum gravity have been proposed and continue to be actively researched, including string theory, loop quantum gravity, and various other theoretical frameworks, each offering its own particular perspective on what might actually replace the classical singularity once quantum effects are properly, fully accounted for. None of these approaches, as of the writing of this particular account, has yet achieved the kind of decisive experimental confirmation that would allow physicists to declare the question genuinely, definitively resolved. This brings us then to the central, honest question this particular chapter must ultimately leave unanswered, at least in any final, definitive sense. Is the singularity predicted by classical general relativity a genuine, literal feature of physical reality, an actual point of infinite density existing at the center of every black hole throughout the universe? Or does it represent instead simply the precise location where our current understanding of physics reaches its own inherent limits, a mathematical signpost indicating not what genuinely exists, but rather the boundary beyond which an entirely different, not yet fully discovered theory would ultimately be required to provide any genuinely accurate description? Current scientific consensus leans, on the whole, toward the latter interpretation, treating the classical singularity not as a confirmed, literal feature of nature, but as a signal of general relativity's own incompleteness when extended into this particular extreme regime. But it is worth being entirely clear that this remains, in the most genuine sense, an open question, one that may not be fully resolved until physicists finally succeed in developing the kind of complete, unified theory of quantum gravity that has, thus far, eluded even the most brilliant researchers working across multiple generations of dedicated, sustained scientific effort. There is something worth sitting with here, something that connects directly back to the very theme that has run throughout this entire account from its opening chapter onward. We have spent this entire journey exploring what can be learned about black holes indirectly, through their effects on light, on matter, on the very fabric of spacetime itself. And here, finally, at the very heart of the black hole itself, at the one location where all of this careful, patient, indirect observation would ultimately need to converge into some final, definitive answer, we find ourselves confronting the genuine limits of what current physics is actually capable of telling us. The singularity remains, even now, genuinely mysterious, not merely inaccessible to direct observation, as everything within a black hole's event horizon necessarily is, but potentially inaccessible even to our most sophisticated current theories, a place where the universe itself may be quietly, patiently waiting for us to develop an entirely new kind of physics before it will finally, fully reveal what actually occurs there. Ahead of us lies one final, closely related mystery, one that emerged directly from the work of physicist Stephen Hawking, revealing that black holes, despite everything we have established throughout this account regarding their absolute permanent darkness, may not in fact remain absolutely, permanently black forever, a discovery that would go on to create one of the most genuinely puzzling paradoxes in the entire history of theoretical physics. In the early 1970s, the physicist Stephen Hawking turned his considerable attention toward a question that, at the time, seemed to most physicists almost entirely settled: whether black holes, having trapped light so completely and so permanently that nothing could ever escape their event horizon, might nonetheless be capable of losing energy over time, through some mechanism entirely distinct from anything we have discussed so far throughout this account. What Hawking discovered through a careful, rigorous combination of general relativity and quantum mechanics, the very two theories whose ultimate unification remains, as discussed in our previous chapter, one of physics' most significant unresolved challenges, would go on to reshape our understanding of black holes in ways that continue to generate genuine scientific debate to this very day. To understand Hawking's remarkable discovery, it helps to recall something particular about quantum mechanics, the branch of physics governing the behavior of matter and energy at the smallest possible scales. According to quantum mechanics, even what we ordinarily think of as empty space is not, in fact, entirely empty at all. Throughout the vacuum of space, pairs of particles and their corresponding antiparticles are constantly, briefly popping into existence, seemingly from nothing before almost immediately colliding with one another and annihilating, disappearing back into nothing just as quickly as they originally appeared, a genuinely strange but well-established consequence of quantum mechanics' own underlying uncertainty, operating continuously throughout the universe, entirely unnoticed under ordinary circumstances. Hawking's crucial insight involved considering what might happen to this same, ordinarily unremarkable process when it occurs very near a black hole's event horizon specifically. Under ordinary circumstances, throughout the vast majority of space, these briefly appearing particle pairs simply annihilate one another almost instantly, leaving no lasting trace of their fleeting, momentary existence. But near an event horizon, Hawking realized something rather different could potentially occur. If such a particle pair happened to form at a location straddling the event horizon precisely, with one particle appearing just outside the boundary and its corresponding partner appearing just inside, the black hole's own gravity could potentially separate the pair before they had any opportunity to annihilate one another as they ordinarily would. The particle that happened to form just inside the event horizon would fall inevitably inward, following the same one-way path described throughout our earlier chapters. But the particle that happened to form just outside the boundary would, crucially, remain free to escape outward, continuing onward into the wider universe as genuine, real, observable radiation. This process, now known as Hawking radiation in recognition of the physicist who first predicted it, suggested something that many physicists at the time found genuinely startling. Black holes, despite everything firmly established throughout this account regarding their absolute inability to emit light or any other form of radiation from within their own event horizon, might nonetheless very gradually emit radiation from the immediate region surrounding that boundary, radiation that would, over time, very slowly carry away a portion of the black hole's own total mass and energy. It is worth immediately clarifying the actual scale of this particular effect, because it differs enormously depending on a black hole's specific size, in a manner that might initially seem somewhat counterintuitive. Hawking's calculations revealed that smaller black holes actually emit this radiation considerably more intensely than larger ones, meaning that the relatively modest stellar mass black holes explored throughout much of this account emit Hawking radiation at a rate almost impossibly slow. So slow that a single stellar mass black hole would require a span of time vastly, almost incomprehensibly longer than the current age of the entire universe, in order to lose any genuinely significant fraction of its total mass through this particular process. The supermassive black holes explored in our 9th chapter emit this same radiation at a rate slower still, given their considerably greater mass. In practical terms, then, Hawking radiation remains, even now, entirely undetected by any existing instrument, its effects far too subtle to measure directly given the enormous, extraordinarily long timescales genuinely involved. And yet, despite this practical undetectability, Hawking's theoretical prediction carries an implication of genuine, profound significance, one that follows necessarily from the basic physics involved regardless of how impossibly long the actual process might take to meaningfully unfold. If a black hole genuinely does emit radiation continuously, however slowly, and if this radiation genuinely does carry away a portion of the black hole's own mass and energy, then given a sufficiently long span of time, far longer than the current age of the universe itself, a black hole would eventually lose the entirety of its mass through this same gradual process, ultimately evaporating away entirely, disappearing completely from the universe rather than persisting forever as an eternal, permanent feature of the cosmic landscape. This conclusion, while genuinely fascinating in its own right, gives rise to a considerably more troubling problem once we begin considering it alongside another, entirely separate and equally well-established principle of quantum mechanics, one concerning the fundamental nature of information itself. According to quantum mechanics, information, meaning the complete, precise physical description of any given system, whatever fell into that black hole across its entire existence, every particle, every precise quantum state should never, under any circumstances, be genuinely, permanently destroyed. Information, according to this fundamental principle, might become scrambled, mixed, or rendered practically impossible to reconstruct given any realistic technology, but it should never, in any truly fundamental sense, actually cease to exist entirely, unrecoverable even in principle by some hypothetical, sufficiently advanced future technology or method. Herein lies the genuine crux of what has become known, within theoretical physics, as the black hole information paradox. If a black hole eventually evaporates away completely, through the gradual process of Hawking radiation just described, what happens to all of the information that originally fell within it across its entire lifetime? Every particle, every star, every fragment of matter that ever crossed its event horizon throughout its entire existence. Hawking's own original calculations suggested something genuinely troubling on this particular point. That the radiation actually emitted by a black hole through this process appeared to be entirely random, carrying no genuine information whatsoever about whatever had originally fallen inside, meaning that once a black hole had fully evaporated away, whatever information it had originally consumed across its entire existence would have vanished from the universe entirely, genuinely and permanently destroyed, in direct, explicit violation of one of quantum mechanics' own most fundamental, most thoroughly established principles. This apparent conflict between general relativity's own prediction that black holes should eventually, inevitably evaporate away completely, and quantum mechanics' own equally firm insistence that information can never be genuinely destroyed under any circumstances whatsoever, represents precisely the kind of situation discussed at length in our previous chapter, two extraordinarily successful theories, each thoroughly confirmed within its own particular domain, producing directly contradictory predictions once extended into a regime where both theories simultaneously become relevant. Physicists have proposed numerous different potential resolutions to this genuine paradox across the decades since Hawking's original work, though it is worth being entirely clear, once again, that no single proposed resolution has yet achieved anything resembling full, universal scientific consensus. One particularly influential proposal, known as the holographic principle, suggests that all of the information genuinely contained within a black hole's interior might actually be preserved, in some sense, on the black hole's own two-dimensional event horizon itself, encoded there in a manner considerably more subtle than our ordinary, everyday intuition would typically suggest, potentially allowing this same information to eventually be released back into the wider universe through Hawking radiation after all, contrary to Hawking's own original calculations, but through a mechanism considerably more sophisticated and considerably more difficult to properly calculate than his original analysis had initially accounted for. Other physicists have proposed alternative resolutions entirely, ranging from the genuinely radical suggestion that our conventional understanding of a black hole's interior may require fundamental revision, to more modest proposals suggesting that Hawking's own original calculation, brilliant and genuinely groundbreaking as it remains, may have simply overlooked certain subtle effects that a more complete, more sophisticated theory would eventually need to properly account for. This remains, even now, more than 5 decades after Hawking's original discovery, a genuinely active, genuinely unresolved area of theoretical physics research, one that continues attracting some of the most brilliant researchers currently working anywhere within the field. There is something worth sitting with here, as we bring this particular chapter toward its close, something that reaches well beyond the specific, technical details of black holes themselves. The information paradox suggests that black holes, rather than representing merely an extreme, exotic curiosity confined to their own particular corner of astrophysics, may actually be pointing towards something considerably more fundamental about the underlying nature of reality itself, the genuine, precise relationship between gravity and quantum mechanics, between the smoothly curved spacetime described by Einstein and the fundamentally probabilistic, discrete world described by quantum theory. Resolving this particular paradox may well require, as many physicists genuinely suspect, nothing less than the same complete, unified theory of quantum gravity discussed at length throughout our previous chapter. A theory that, once finally developed, may end up revealing something profound not merely about black holes specifically, but about the fundamental structure of the universe as a whole. Ahead of us lies our account's final chapter, one that will draw together everything explored across these 13 preceding chapters, returning us, finally, to the same profound silence with which our entire journey first began. We return in these final moments of our long account to precisely where we began, complete, unbroken silence, the same vast, cold quiet that fills nearly all of the universe between one star and the next. It is worth sitting with that silence once more, now that we have spent 13 chapters carefully, patiently filling it with everything we have managed to learn. A massive star somewhere in the depths of a galaxy not so different from our own spends millions of years locked in its own quiet, ongoing struggle, gravity pulling relentlessly inward, nuclear fusion pushing steadily outward, a balance that feels, for as long as it holds, almost permanent. And then, inevitably, that balance breaks. The star's core, having exhausted every stage of fusion available to it, collapses in on itself within a matter of seconds, an entire lifetime of stability undone in less time than it takes to draw a breath. Gravity, patient and relentless, finally wins. From this collapse, an event horizon forms, a boundary defined not by any physical substance, but by the simple, absolute mathematics of escape velocity finally exceeding the speed of light itself. Light disappears not because it is somehow destroyed, but because it has become trapped, its outward path bent by curved spacetime so extreme that no direction remains that leads away rather than inward. And near this boundary, time itself begins to behave in ways that defy our ordinary intuition, stretching and slowing depending entirely on one's particular vantage point, two equally true perspectives on the very same event, each valid within its own frame of reference. Around this same boundary, matter unlucky enough to wander two close spirals inward, heated by friction to temperatures reaching into the millions of degrees, glowing with such tremendous intensity that it can outshine entire galaxies, forming brilliant, blazing disks around objects that remain, at their very center, absolutely and permanently dark. Some of this same superheated matter, rather than continuing its inward spiral, finds itself instead launched outward along powerful magnetic fields, forming relativistic jets that stretch across distances vast enough to span the very galaxies that contain them, transforming an invisible gravitational anomaly into a beacon visible across billions of light years. At the very centers of galaxies, these same black holes grow to a scale almost impossible to properly comprehend, millions or billions of times more massive than our own sun, quietly shaping the orbits of stars and quite possibly the broader evolution of the very galaxies that surround them, their presence confirmed not through any direct glimpse, but through decades of patient, careful observation of everything nearby that their gravity so unmistakably influences. And sometimes, across a span of time stretching potentially into billions of years, two such black holes find themselves drawn together, locked in an increasingly rapid gravitational dance that ends, finally, in a merger of such extraordinary violence that it sends ripples outward through the very fabric of spacetime itself. ripples that patient instruments here on Earth have now learned remarkably to detect, and even when converted into sound, to genuinely hear a brief rising chirp marking the final, silent collision of two objects that neither light nor any other conventional signal could ever have revealed. Beyond all of this, beyond the accretion disks and the jets and the gravitational waves, our direct knowledge finally, honestly, ends. What actually occurs beyond the event horizon, whether a genuine singularity of infinite density truly exists at a black hole's center, or whether that singularity instead marks simply the boundary of our own current understanding, remains a question current physics cannot yet fully answer. And even the eventual fate of a black hole itself, its slow, almost unimaginably gradual evaporation through Hawking radiation, and the fundamental question of what becomes of everything it ever consumed, remains genuinely unresolved, a paradox at the very heart of modern theoretical physics, one that may not be fully settled until an entirely new understanding of gravity and quantum mechanics finally, successfully, comes together. We have, across these 14 chapters, learned a considerable amount about these strange, silent objects. We understand how they form, from the violent, spectacular death of a star far larger than our own quiet sun. We understand the physics of their event horizon, the strange behavior of time in their presence, the brilliant light that surrounds even the darkest possible object the universe can produce. We understand, too, the genuine limits of what we currently know, the honest, unresolved mysteries still waiting somewhere beyond the boundary of our own best theories. Perhaps the most frightening thing about a black hole, when we finally sit with everything we have learned across this long account, is not that it destroys everything that crosses its horizon. Destruction, in some sense, is a fate the universe meets out to nearly everything, given sufficient time. What feels considerably stranger, considerably more genuinely unsettling, is the quieter fact sitting just beneath it. That beyond that horizon lies an entire region of the universe, permanent and physically real, that we may never actually be able to see, not through any lack of effort or ingenuity, but because the very nature of the boundary itself forbids it, absolutely and permanently, regardless of how sophisticated our instruments might someday become. And yet there is something else worth carrying forward from this same realization, something considerably less unsettling, and perhaps even something quietly comforting, particularly as you drift now toward your own rest. The universe, for all its overwhelming scale, for all its genuinely extreme and sometimes frightening physics, remains something we continue to patiently, carefully understand, one careful observation at a time, one indirect clue at a time, light bent around an invisible boundary, stars traced in careful orbits around an unseen center, ripples in spacetime finally, remarkably, converted into sound. Black holes, the quietest, most silent objects the universe contains, have nonetheless told us an enormous amount about themselves, not despite their silence, but through everything that silence has left behind. Somewhere out there right now, as you rest, a black hole continues its own quiet, patient existence, indifferent entirely to our efforts to understand it, asking nothing of us, offering nothing directly in return, and yet revealing, to anyone patient enough to look carefully at everything surrounding it, some of the most profound truths our universe has ever offered about gravity, about time, about the very fabric of space itself. Let that quiet, patient darkness be the last thing on your mind tonight, not something to fear, but something to simply wonder at, vast and silent and endlessly strange, exactly as it has always been, and exactly as it will remain long after we are gone.